Hello, hello. Yeah. What time do we have? Okay. All right. So good afternoon and welcome back to DSP. And so we will continue from last week. So remember the last Thursday we had a discussion session, right? And we were looking at DTFT, discrete time Fourier transform. And so in that discussion session for homework number 1, you got a chance to deal with both the forward and the forward transform and the inverse transform. Forward transform from time to frequency, inverse is from frequency back to time. Okay, so this is a version, 一种版本, a Fourier transform that was defined on discrete time sequences. So today we are going to continue and just to in case you have already learned DTFT before, most likely from signals and systems, this will be a review. But for those of you that are, some of you this might be new, but selected properties. So here I say selected property, 选择性的啊. So we are not going to my intention, 我的目标啊. My intention is not to cover everything there in DTFT, but instead I choose to focus on just a few properties that I found most useful for the rest of the semester. So there will be a discussion on selected properties of the transform, with that, let me first let's just look at the definition again. So for any time domain signal x of n, being a sequence of number, n, let me emphasize one more time, n is an integer. Okay? N is a time index, and by default is an integer. So xn, we multiply it with e to the minus j omega n. Here the variable small omega is the frequency, which I recommend is, we use it around the unit circle. So let's say from 0 to 2 pi, or if you will, from minus pi to pi, because it's gonna, later you will learn that it is periodic, okay? So doesn't matter, omega is any interval, any closed interval 2 pi, from minus pi to pi, or from 0 to 2 pi. So omega is the frequency. So last time I spent a few moments to share with you that there is a conversion between small omega and big omega. And you need to know that small omega has it doesn't have a unit. Or if you really want, then the unit, I would say the unit of small omega is radian per sample, which means how much of a phase change is introduced by going forward in time from going from n to n plus 1. If you move in a time domain by one sample, how much phase change is there? That's the meaning of small omega. Okay? But whereas big omega really has a unit of radian per sample, per second, radian per second. So which equals to 2 pi times hertz. 2 pi times frequency in hertz is the big omega. Okay, so just to summarize, so here's my recommendation. Just please learn to get used to this. Okay, whenever we sample a signal, so it becomes a sequence. Now time index becomes 1, 2, 3, 4, 5. Right. So now the relation between small omega and big omega really is a factor of t. So they are, of course, proportional, right? So last time we spent a few moments to talk about this particular example where we define the sampling rate. If the sampling rate is given to you, it's 48 kilohertz, then when we look at this frequency small omega, if it's pi divided by 6 or 30 degrees, 30度, pi divided by 6, pi over 6, and you will just learn quickly that it should correspond to 4 kilohertz. 4 kilohertz. And the way I remember it, do you remember how I remember it? So I said that almost I just automatically, whenever I see small omega, I think of pi as the Nyquist rate, because pi is 1/2 of 2 pi, and 2 pi corresponds to the sampling rate, right? So pi corresponds to Nyquist rate, which is half of that, equals to 24. Therefore, you can calculate quickly any given frequency small omega. We can calculate quickly how that corresponds to a frequency back in hertz in the time in continuous time. Okay? So there's a simple relation over there. You should be aware of. 你需要知道, you should be aware of. Any questions so far? That's from last time. And the inverse transform is something that we introduced right away last time. Okay, when we have the forward transform, we have the inverse transform. You can easily check that indeed, if we are given the definition of big X, a spectrum. So what we do here, in this definition, we take the spectrum and multiply it by e to the j omega n, because the spectrum tells us how much of the signal is there at this particular frequency, right? And one particular frequency, so this is a complex valued coefficient, and then we multiply it with ej omega n, which can be regarded as a small wave, and then we accumulate all the frequency over small omega, and there should be a normalization factor. You don't want to forget that. And you can easily check mathematically that indeed, when we just do this calculation, it gives us back, this is what we get. We get back the signal in time, okay, by starting with the spectrum. So this is an inverse transform, which goes from frequency domain to time domain. Okay, inverse transform, and we have checked that. So today, in the next few slides, I would like to talk about my selected properties. And you can find these properties on the textbook for sure. In the textbook, you just check these two sections, okay? Check those sections and you'll find a more complete coverage of all the properties that are known for discrete time Fourier transform. But first one, I'd like to mention that our spectrum, when we talk about DTFT, the spectrum is going to be periodic. Periodicity, 周期性, it's going to be periodic. And so that's an easy property. And you can just, by looking at the definition, you should notice that. So I want to just summarize that the first property you should be aware of is periodicity. The 2 pi, any spectrum for DTFT. This will not be true for general Fourier transform, not true. But for discrete time Fourier transform, when we use small omega to denote the frequency, this spectrum is periodic. Every 2 pi, the spectrum repeats itself. Okay, some of you also pointed out last Thursday when we met for discussion. Yeah, of course, they are periodic. So that being said, I often told my graduate student, okay, when you plot DTFT, there's no need to repeat, okay? If I asked you to make a sketch for your homework or for your tests, if I ever ask you to sketch a magnitude spectrum for any DTFT, please, you can just plot from 0 to 2 pi, something, okay? Or you can plot from -pi to pi. And that'll be great, okay? Yeah, for the same thing, actually, sort of the same thing. There's no need to repeatedly plot beyond a period of 2 pi because the spectrum itself is guaranteed to be periodic. Okay? There's no exception. There's no exception. Okay? So let's say if I ever asked you to plot the magnitude spectrum of a signal, then just plot it with an interval of 2 pi. That will suffice. 那就够了. That will suffice. Periodicity. Can we move on to the second property? Okay. The second property is also quite important. So I recommended to you that in this classroom, in this entire semester, unless we mention otherwise, unless we mention, so if we don't mention, then we assume that our signals in time is real valued. Real valued. 它的值是实数的 real valued. Unless we mention otherwise. Unless we emphasize, this time xn is complex number. Okay? Otherwise, if xn is real to begin with for all n, then we have this symmetry property, number 1. Number 2 and number 3 are both symmetry properties, 是对称性的, about symmetry. The first thing, number 2, if time domain is real, then what we have here is that when we evaluate the spectrum at minus omega, that's where I read it. If we evaluate, 去计算, 去评估, if we evaluate the spectrum at minus omega, then the result is going to be the spectrum at plus omega but conjugated if the signal is real to begin with in the time domain. Okay? And we can easily check that. Okay, let's check this. Number 2, is it really the case? Number 2, check. So easy enough, we are going to evaluate our spectrum in the negative omega, at negative omega. So by definition, we apply the definition is, sure, we have xn e to the minus j, but minus omega n, and we sum over all n, and where we assume xn is real to begin with. So that's the meaning of evaluate the spectrum at minus omega according to the definition, right? And what's next? Apparently, minus and minus, we have a plus, right? So next step, of course, this is xn e to the j omega n. And this is, of course, summation n, x of n, e to the minus j omega n conjugate. And here we do take the assumption that xn is real, that x, the signal, is real. Then just conjugating the sum equals to the sum of conjugating individual terms. That's right there. So here we finish the check. Okay. Indeed, when we evaluate the spectrum at negative frequency, then it's going to be the same as if we are evaluating it in the positive frequency but conjugated. Okay. So that's the symmetry. When we replace omega with minus omega, then the result is complex conjugate. Okay. 共二复数啊，叫 conjugate 这个字啊 ，conjugate. Let me just write it. Conjugate. That's in Chinese is 共二复数啊 conjugated. Yeah. Okay. So what's the implication? What's the implication property number 2? If I ask you to plot the magnitude spectrum again, for a signal that you know is real, then what's the consequence? 后果是什么? What's the consequence? Do you really need to plot from 0 to 2 pi? The answer is no. Or this should be clearer. Do we need to plot from minus pi to pi? The answer is no. Why? because of the left and right, the magnitude spectrum will always be evenly symmetric. Yeah? When you flip the spectrum left to right, it's always the magnitude spectrum, the magnitude spectrum. So there's a kind of a consequence. Let me write it. Okay? Because of number 2, so therefore, x, e, j minus omega, when you evaluate the magnitude spectrum at negative frequency, negative omega, it's going to be the same as evaluating this, right? What's here is equal to what's here, right? We're just taking the magnitude, taking the absolute value. But then, what's the absolute value of a complex conjugate of any complex number? It's the same, right? It's the same. The absolute value of a complex conjugate to any complex number is the same, right? Remains the same. Therefore, we have this so we obtain the result. When we evaluate the magnitude of a spectrum at minus omega, the result is going to be the same as the magnitude spectrum at plus omega. In other words, the magnitude spectrum, when we take the absolute value with the magnitude spectrum, it's going to be evenly symmetric. It's going to be evenly symmetric. So therefore, if somebody just plot this, let me just erase. If you just give me this plot, I give you full credit, okay? 这也是满分的啊。As long as our signal is real in the time domain. As long as our signal is real in time domain, which most likely will be the case. Right? So that's sort of a kind of a practical consequence of this nice property. So this symmetric, so you don't need to plot the negative part because it's always going to be symmetric. Okay? I'm not doing a very good job, but you know what I mean. All right, so that's property number 2. Symmetry in the frequency domain. But how about now symmetry in the time domain? We know that in Fourier transform, a lot of times we have a property in the time domain, we have the equivalent property in the frequency domain. And you can call it duality, 对偶性，有这种的 duality. So if we have a symmetry property in the frequency domain, how about in the time domain? If we assume that our signal is real and the signal itself is evenly symmetric in the time domain. So given these two conditions, it turns out that you can show that the spectrum is going to be real valued. In other words, there will not be the imaginary part. The imaginary part of that spectrum is going to be 0. Purely real. Okay? So I leave the proof as an exercise. Okay? So, but keep in mind that whenever we have a symmetry property in the frequency domain, you have the corresponding property in the time domains. This is one example of duality. The duality of Fourier transform. This probably will be useful later on when we design filters. I can promise you, we will use it. We will use it. Kind of a nice property. And can I move on to the next property? Okay, this is the shift theorem. Okay, the shift theorem, where we have this notation. Let me introduce this slowly. Okay, so here we assume that there's a signal x for sure, but if we define another signal y, if we define another signal y which equal to x evaluated at n minus a fixed number m. Okay, so let me be clear that here m is a fixed number, n is an index. N is index 1, 2, 3, 4, 5. Okay, and m is a fixed number, a fixed integer. Could be positive, could be negative. But m is a fixed integer, right? So by this definition, hopefully we can imagine that what's the relation between y and x. Y is just x delayed by m samples. Can we agree on that? Y is just m delayed, 延后的, delayed by m samples. M could be 3, m could be 100, m is a fixed integer. Okay? So if y is simply x but delayed by a few samples, by m samples to be exact, then we have this relation. Then we have the relation that the spectrum of y is going to be x, but multiplied with this extra term right there, multiplied by a fixed complex number. Okay? Multiplied by that. I'm sorry, not a fixed number, but I mean m is fixed, but omega is still there. Okay, multiplied by this term, we can call the term a linear phase term. A linear phase term. Okay, so let me write this down. Let's have a brief discussion on this property. Let me, just erase this part. Shift theorem. And by the way, in tomorrow's discussion, I asked you to sign up. This is the first question for tomorrow's discussion. I'll ask any volunteer, if you will, come here to show that this is true. Okay, but here I would want to introduce, share with you kind of a physical insight, what's going on here. When we shift a signal by m samples in time, it introduces a phase change for every frequency. And that phase change is e to the j omega. That phase change is omega times m. Okay? So let me point out. So if this is true, we are going to show it tomorrow in the discussion session. But here is my insight. If this is true, let's assume that this is true. Okay? Let's just for the moment agree that this is true. And what does it tell us? Here's my insight. We can take the phase of the spectrum. Right? We can take the phase of the spectrum. We take the phase of the spectrum. And we know that when we multiply two complex numbers, what happens in the phase? When we multiply two complex numbers, the phase adds, right? The phase is summed. The magnitude will also multiply, but the phase is summed. The phase add on top, right? So we get this result. We get, this is complex number, it looks like that, and plus the phase of the original, the spectrum of x, big X, okay? So far, so good, okay? The phase will have this summation relation. But there is an interesting property called group delay. Group delay. So it's defined as partial. When we take the partial derivative of a phase spectrum with respect to frequency, this quantity, and there's a minus sign, is called group delay. I shouldn't say group delay. I mean, anyway, let me just for the time being say it's group delay, okay? So that's a definition that's that we evaluate for y. Okay? For any spectrum y, we can evaluate its first derivative of the phase with respect to omega. Okay, phase on top, omega at the bottom. Okay. So if you do that, there's a negative sign. Then we are talking about partial here, partial omega plus partial x, the phase spectrum of x, also with respect to omega. So there's a simple equation, right? If this is true, if that's true, this is true, then this should be true. The equality should hold over here. Okay? So what do we have? So what's here? What's the phase of e to the j something? It's simply the exponent, right? You need to be careful. The exponent omega m, right? So yeah, well, watch me. So so here equals to omega m. Okay, is that clear? Yeah. The phase equals to omega m. I'm sorry, there should be a minus sign. Yeah, not omega m, but minus omega m. Yeah. Minus omega m. Yeah? And then when we take the derivative of minus omega m with respect to omega, so what do we get? We get m, right? We get minus m. So we have minus m, and let me just still copy that term over here, over there. I close the bracket, the brace, and then this becomes an interesting property. Okay, so now here, minus we have m, and plus what? Plus something. So that means the group delay for y, for that y in the time domain in the frequency domain, the group delay for y equals to m plus the group delay for x. Yeah. So this is for y. This is for x at every omega. Yeah. So that makes a lot of sense. Why? Because if you so group delay of a signal means that how long you need to wait for the sort of the center of a signal to come. Okay. So we'll go back, come back to here. Okay. So so there's a kind of deeper insight in probably in the shift theorem. It makes a lot of sense. When we delay our signal in time by m samples, then in the spectrum, what will we will get this result. In the spectrum, we found that at every frequency, the group delay is going to increase by m. Why? Because we delay the signal in time by m samples. Okay? So that means every frequency component is going to come m samples later. That's the meaning of group delay as a function of frequency. Yeah. Yeah. So there's no contradiction. Okay, so so everything put together, they all make sense, right? So yeah, so that much we can say about talk about this shift theorem, which will be discussed tomorrow, and also we are going to now move on to the next property. Right? Next property is the convolution theorem. Okay, the convolution theorem. For anybody who needs to take a picture, maybe now it's time before I erase it. Okay, picture break. Yeah, picture break. Yeah, let me go to that side. So with that, with the very useful shift theorem, then now we can officially talk about the convolution theorem. Okay, the convolution theorem goes like this. Okay, so here we are talking about two signals in time, and we want to calculate what is called convolution of the two signals. So let's denote one of the signal as x, the other as h. Okay, x and h. And we use this notation, x convolve with h. And here, this is my preference, what prefer. My preference of how we denote convolution. I want to emphasize that x is a signal, h a signal, and convolution as a result is also a signal. So this is my notation. X convolve with h, and which will be a signal. That's the meaning. Right? This is why I use this notation. You might not find it in the textbook. Right? But just to emphasize that the result of convolution is a signal. Okay, is a signal. We're taking two signals, and so the definition is a summation over k, and is a sum of products. A sum of product, and for every n, we would flip one of the signals. So note that here, h goes backward. If we as far as the summation is concerned. Inside this summation, x, k goes forward, but h, there is a minus k, h goes backward, okay? So we flip h and shift by n, and then evaluate, we sum all the products. We sum up all the products over there. That's the definition of convolution. That's the definition of convolution. So here, as I just to sort of go through, why this definition is called the convolution of x, signal x, and signal h. And next, I'd like to point out that please note that convolution is commutative, 具有可交换性 commutative. Doesn't matter. X convolved with h equals to h convolved with x. You can check that. Convolution is like addition, like multiplication. 就像加法跟乘法 Convolution is also commutative. 是具有交换性的 commutable. So it doesn't matter x convolved with h or h convolved with x. The two of them are equal for any arbitrary sequences x and h. All right. So now the convolution theorem goes further. What happened? The issue here is what will happen in the frequency domain. What will happen in the frequency domain? When we convolve, we take the convolution of signals in time. What happens in the frequency domain is multiplication, even simpler. So we convolve in time. So it turns out we will show that, we can show that, and we will show that in the frequency domain, we take the product of two spectrums, and the result is the spectrum for the convolution. You take convolution in time domain, the result that the consequence is that the two spectrums will multiply in the frequency domain, right? For all omega, and this property is called the convolution theorem. Okay. And convolution theorem is gonna show up everywhere throughout the semester. When we talk about systems, when we talk about any linear time invariant systems, okay? So in this semester, we will just mostly use h to denote the impulse response of a system, where x will be our input. So just to put this thing into a bit of context, we would often talk about a linear time invariant system which has an impulse response denoted by h. Okay, impulse response is a system. The impulse response of a system. So the context often goes this way. If h is the impulse response of a system, and then we take x as the input, then the result is going to be x convolve with h. X convolve with h. Yeah. So that's the most often the number one context in which we use the convolution. We think about the convolution theorem. Okay? We'll come back to this. Okay? We'll come back to this. Now, next, I would like to invite all of you to work with me through the proof of convolution theorem. Okay? Let's work on that. So, convolution in time domain, multiplication in frequency domain. How come? Yeah. Let's make a derivation. right? Shall we? Let me just stay on this side. Okay, so we want to evaluate y ej omega. And what is y ej omega? But y ej omega, the spectrum, by definition, is a DTFT of signal y in the time domain, right? So by definition, it should be equal to summation n, yn e minus j omega n. That, right? Yeah. But then what is yn? Yn is suppose that y is x convolve with h. So yn, what is yn? Yn is a summation over all k, right? Convolution xk h n minus k. That's y in time domain by definition. Okay? And we copy this term right here. So what's next? Almost always when we see summation, double summation, what can we try? Changing the order, right? We try changing the order. So we put k outside, and n inside. So anything that has nothing to do with n can be put to the outside, which is this term right here. While in the inside, now n goes inside. Summation over O goes inside. It goes inside, and then let's just write down everything that depends on n. Okay, so that which is this. Okay. So what do we notice? What did you notice? What do you notice? Here looks like what? It looks like the Fourier transform of something, right? It looks like a Fourier transform of one thing. What's that thing? The thing is h shifted by k samples, right? So here we are going to apply the shift theorem. This is the place where we can apply the shift theorem. So here, because of shift theorem, we know that this term equals to what? It equals to the spectrum of h, but with a linear phase term. With a linear phase term, as far as n is concerned, k is the fixed number. So here, e minus j k what? jk omega. Or j omega k, if you will. Okay. E to j omega k. Okay. So we can continue, right? Now we can continue. So you are probably seeing the result. You're getting close, right? Are we getting close? Yes. Now we copy everything here, still summation over all k. xk is copied right here. But here now, what do we have? We have e to the minus j omega k. And then we have one thing right here which does not depend on k. Right? That thing over there does not depend on k, and that's almost the end of derivation. Okay? I say this is going to come to an end because why? Because what do we have here? What's here? What's showing on here? What's showing right here? Summation over k, and k is just a dummy index, right? A dummy index. So this is exactly the spectrum of x. This term equals to spectrum of x. By definition, that's the DTFT of x, evaluated at omega, where k right here, don't worry, it's a dummy variable. Okay? Yeah, so now we have, on the left-hand side, we have y, big Y. On the right-hand side, we have the product of h and x and h. So that finishes our check on a proof of a concise proof of a convolution theorem. Okay. So far so good. Yeah. Is this good? Okay. Yeah. So I think that's a nice exercise to review once in a while. Yeah. Convolution theorem. We come back to this is super useful. Okay, convolution theorem has a lot of meaning in this context, in the context of studying systems, studying linear systems. Yeah, we come back to that. Okay, so next thing, this is a bit quick, but this next thing is a beautiful theorem. Okay, perhaps one of the very nicest theorems that we'll encounter in the entire semester. So I would love to share with you. We need to know that there's a thing, a theorem that's related to energy of a signal. The energy of a signal. So let's look at the result first, okay? There's an identity, 一个恒等式 identity. This is an identity which applies, which is true for any given signal. Okay, for any given signal x. Yeah, if we sum up the square of x, I mean square of the absolute value of x, sum them up in the time domain, the result will basically be equal to integrating the magnitude spectrum also squared in frequency. This is an identity. 是一个恒等式. This is an identity which will hold for any given signal. Okay. The only there is a scaling factor that cannot be abandoned. There's indeed a factor of 1/2 pi, but essentially, 本质上, this tells us energy can be calculated in the time domain or in the frequency domain, and that's very nice. Okay, and the total energy of a signal. Okay, so I say energy. I mean, if we agree that this summation can be called energy. If we call this energy, and that also makes sense. The reason we call this energy, so let me make a remark right here. We sum over all n, and when we sum over x squared in time, so that's is like so let's say we have a x c of t in continuous time to begin with, right? And the unit might be volt, yeah. Okay, unit might be volt. So the idea is that if we let's say we just simply think of this as if it will go through a load of resistor, which has a resistance R, right? So if this is a voltage across a resistance, then what's the total energy dissipation? 什么 R 分之 V 平方 yeah, V squared. Thank you. So V squared divided by R, what is that? What's the unit of this? What's the unit of this? V squared divided by R. A power, right? It's a power. So we just take the integral of that from 0 to, let's say, to forever, yeah, dt. So that's the entire power assumption, power dissipation by the resistor R, right? So there's a kind of a connotation that when we take the square of a signal, that's directly related to power, to the power that the signal is providing, right? And when we sum up power in time, or when we take an integral of power in time, which in discrete time is going to be equivalent to summing up the square. So that's why we kind of loosely just borrow the term energy. Okay, we loosely when this is 把那个名词借过来啊 so we'll borrow this terminology energy to refer to the sum of square. Okay, sum of square. But in practice, you can imagine such kind of things. Okay, sum of square. in time equals to sort of the integral of square in the frequency, and there is a factor of 1/2 pi. Okay, so energy. So the kind of message right here is an implication. Energy can be calculated in the time domain or in the frequency domain. The result is going to be the same. Okay, only difference is a factor of 2 pi, not super important. Okay, which is not that important. But any comment? If you ever wonder why the professor thinks this is a beautiful theorem, in what regard? 在哪方面? In what regard is this beautiful? Beautiful, yeah? 增加是不是？能量守恒 conservation of energy. That's a nice way to say it. Or any other? Why do you think might we think that this is beautiful? 没有标准答案啊，就是Any other suggestion? Any other comment? Why do we think this could be beautiful? Anything that fits in one line is beautiful, right? Yeah. Yeah. Oh, using the. Oh, that's interesting too. Yeah, that's an interesting observation. So there might be a concern. You might be right. There might be a concern if this thing doesn't converge, then 就拉倒. then there's no such. So we need to add a constraint. If this converges, then it converges to this integral. So that's beautiful too. Any other insight that anybody would like to share? Why do you think? Why should we think? Why can we think that this is beautiful? So I think I would like to kind of refer to linear algebra. Okay? Let's refer to linear algebra. So in the language of linear algebra, we say Fourier transform, blah, 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 点点点. Fourier transform preserves the norm. 保持范数, preserve the norm. That's my point of view. Fourier transform preserves the norm. And that's a terminology in linear algebra. Let me point out that this theorem shows that Fourier transform, and in this case, a discrete time Fourier transform. Discrete time Fourier transform, discrete time Fourier transform preserves the norm. Preserves the norm. What is norm? What is a norm? Norm is about taking the inner product of a vector with itself, right? Does anybody remember? For those of you that have taken linear algebra, when we take the inner product of one's vector with itself, that's defined as norm square. Norm square. Okay. So just in case that you might be familiar, let's say V is a vector which belongs to a vector space big V, and just we can endow the space with, we can define inner product, which is usually denoted as a left, right, angle and V. Yeah. When we take the inner product of a vector in any given vector space, that is a definition of norm square. Okay, norm square. So I'm just sharing with you that this is a kind of norm square. This is like we are taking the inner product of our signal with itself in the vector space of all signals. In the vector space of all signals, for which this summation converges. Yeah. So this is, just long story short, you can appreciate it as a kind of norm square. This is the result of taking the inner product of our signal with itself. much like any finite length vector, right? What is the inner product of the vector itself? You sum over the square of all the components, right? So this is a kind of inner product of a signal with itself. Norm square on the left-hand side. And what's on the right-hand side? The right-hand side is just to take a similar operation, but in the frequency domain. Okay. So for any, let's say for any x and y. For any true signal, we can define x, y, the inner product as, probably the correct definition is x and y conjugate n, right? For a complex valued signal. For real, you don't need to worry. But similarly, in the frequency domain, we can also make a similar definition. Okay? We can make a corresponding definition. We can also define in the frequency domain when we have x and y, we can define inner product in the frequency for spectrums. For any two given spectrums, we can define the inner product of two functions, two continuous frequency functions. Okay? You can define the inner product as integral minus pi to pi x y conjugate d omega. So inner product on the left-hand side, inner product on the right-hand side. Okay? And if you are talking about inner product of something with itself, that becomes a norm square. Norm square on the left-hand side, norm square on the right-hand side. And what's the relation right here? What's the relation? The relation right here when we look, take a look back at this, focus on this equation. Okay, so when we just take a look again at the equation, at this identity, it tells us that by going to the frequency domain, the norm square becomes is essentially preserved, 是保留的. The only difference is a factor of 2 pi. But otherwise, there's an identity. Okay? And I think this is beautiful. Fourier transform preserves the norm. And this property has a lot of implication. Okay? This probably has any questions so far about, this is a lot of extra materials that I'm sharing. Okay? Yeah. Let's take a break. It's about time. Let's take a 下课. Let's take a 10-minute break before we come back and complete this and finish this lecture. Hello, 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 yeah. Hello. So speaking of the beauty of 19th century mathematics, 19世纪的数学, beautiful stuff. Yeah. So just I thank some of you for a comment on looking the way we look at this identity. Right? Let's come back to look at Parseval's theorem. I say it preserves the norm, and this is a special property. Okay, why? Because Fourier transform can be regarded. I want you to remember, Fourier transform can be regarded as a change of basis. 傅列转换是坐标变换啊 a change of basis from time domain, and now we choose a different basis set, different basis. 基底的这个变换 the basis is going to be the set of all e to the j omega n. Yeah, change of basis. Now, so that the index changes from n to omega, right? Think of it as a change of some change of basis, okay, for any vector space. Yeah, and we know that when we all know that for any vector space, the basis is not unique, right? Generally, basis can be changed, right? It's not unique. 并不是唯一的. There are multiple ways of representing a vector using a different set of bases, right? But here, in general, when you change basis, then you calculate the norm, the result is going to change, right? Because you can stretch in one dimension and compress it into the other dimension, and the length of the vector is not going to be 1 over 2 pi times the original length. Whenever you change a basis, most likely, generally speaking, the norm is not preserved. But here, Fourier transform is a special kind of change of basis which preserves the norm. So this is special. This is worth noticing, okay? Worth mentioning. It's special. In general, any change of basis will not preserve the norm. So that's one reason I say it's beautiful in the from the angle of changing basis. Right? When we think of Fourier transform as a change of basis, you're representing your signal in the frequency domain. That's a change of basis. Fourier transform preserves the norm, and so this is indeed one thing I want to mention to you, but. Otherwise, in the textbook, this is some additional remarks I want to also mention to you. If you're interested, there's some materials you can extend your reading, okay, about DTFT. So DTFT here, if you talk about the existence of DTFT, we are not talking about, okay, existence means that the summation converges or not. Okay? If the summation converges, then we call, the Fourier transform exists. So here's the first notion. The first notion gives us a sufficient but not necessary condition for DTFT to converge. So let me read it first. So this is a known property that if x in the time domain is absolutely summable, absolutely, when we sum up all the absolute values of all samples, when the signal is absolutely summable, less than infinity, absolutely summable, then this sequence, that's the definition of DTFT, by the way, right? Let's notice, please be aware that this is the definition of DTFT. If the x is absolutely summable, then DTFT converges for any omega. Nice. Sufficient, okay? Sufficient to guarantee that DTFT converges, so there's no worry. It can be calculated, it exists. So that's a notion of existence. 所谓的存在, in this context, what we call existence just merely means that we are asking whether or not this summation converges. Okay? And there's a sufficient condition right here. If this happens, no worry. Okay? DTFT can be calculated, it exists. And that's the first notion. The second notion is, if you look at it briefly, you might find it absurd. 看起来很蠢啊. This might look absurd. absurd. It's a nice word. Today's 公众英语教室啊。Absurd. It might be a little bit absurd, stupid to look at first, right? But so let me explain. The second notion is that, well, what if x is not absolutely summable, right? We have said that if x is absolutely summable, then no worry, DTFT exists, right? But what if it is not absolutely summable? Can we still talk about DTFT? That's a valid question. That's a valid concern, okay? That's a valid concern. Well, so there's now 19th century mathematics tells us that if x is not absolutely summable, if it diverges, if this diverges, but the sum of square converges, all right? Yeah. Then we just need a more careful definition of DTFT. Okay? Then let us define DTFT as the limit, a limit. Limit of what? The limit of taking this finite summation first, then let big N let it go to infinity. Looks stupid, right? Right. That's a second notion. It's a worry of a kind of rare case. What if the signal is not absolutely summable, but the square of a signal is absolutely summable? Then we can refine our definition. Just be a bit more careful. Be a bit more careful. We define DTFE as the limit of a finite sum. And then we first evaluate the finite sum here, negative n to plus n. That's an important detail right here. Okay? If you define DTFT as such, then still there's no worry. Then this converges. Okay? Then this very definition, this newer, slightly more refined definition, converges for all omega. Okay? So this is kind of first transform is deep. This is so just in case you're interested, just talk to me. Right? So why do I think this might look a little bit absurd to be at the beginning, right? But the textbook has you can find this kind of discussion also in the textbook, right? But this is optional, right? So with that, I would like to just conclude our kind of a brief introduction of selective properties for DTFT. What do we have? Periodicity, 5 properties, right? Periodicity, symmetry, 2 kinds of symmetry, and the next is convolution theorem, shift theorem, and the Parseval theorem. So those are the selective properties I'd like to sort of summarize in one lecture, right? With that, any comment? Yeah. Talk to me if you are interested, because I am. I'm interested in that. Right, so let me now switch to my next lecture. Okay, my next lecture is already posted. You can download it from EE class, lecture number 4. Lecture number 4. Okay. So, yeah. So now, I'd like to switch to a new topic, okay? This is the last lecture of this on chapter 4. Okay? In chapter 4, we're all about sampling and the relation between discrete time and continuous time, okay? But there's one last issue, important issue, that we need to talk about, really making the signal digital. The signal can be make digital so that we can process it with computers, right? We need to represent numbers by digits. Yeah. So digital signal, just if you want to be sure, a digital signal has to be, you need to talk about how we represent numbers. So this is the time we talk about number representation. Okay, how do we encode a number, any real number, by let's say 8 bits, 8位元. How do we do that? So let's take a kind of a review, a summary on that. So this lecture is about finally making the signal digital, and then we can talk about digital processing of analog signals, and there the main issue is called quantization. When we encode any real number, that encoding introduces error. Just inevitably, 无可避免, when we just represent a real number by finite resolution, by just 8 bits, 16 bits, 32 bits, 64 bits, just inevitably there will be an error of rounding. 做四舍五入的时候, we'll see that basically to encode a real number, we recommend using rounding. Okay, 用四舍五入. But then after 四舍五入, after rounding, the fractional part, 小数的部分 is abandoned, right? So that introduces a kind of error, which we call quantization noise. Error is noise. Error is noisy. Error is unwanted. Okay. Yeah. So with that, let's come to the first slide. So this first slide is a sort of a review. Here on the left we have a continuous time signal, and we can just convert it to discrete time, and the result becomes a sequence of number with, and then here you can also specify a sampling rate, sampling period. And everything can happen in the discrete time domain. And then in the end, you might want to we want to just output your signal. Okay, so that is to say, you might want to convert your signal from discrete back to the continuous time using the same sampling period. Okay, so this chain of processing is called discrete time processing or filtering of continuous time signals. Yeah. But now, that's a kind of ideal scenario. It's too simplified. 太过于简化, too simplified. So it does not talk about how we actually represent the number, right? The numbers. So here is a more complete chain of blocks that we need to be aware of. So first of all, still, with the continuous time signal, because we want to prevent aliasing, you need to low pass the signal first. Okay? Low pass to ensure that the bandwidth is what? Narrower than 1/2 of your sampling rate, right? So this first preliminary step is called anti-aliasing. Anti-aliasing, you don't want to apply a low pass filter. Make sure the bandwidth now here is less than or equal to 1/2 of a sampling rate, okay? All right, so after anti-aliasing filter, then to convert to discrete time, there is sample and hold, which we'll explain in the next slide. That's the next step. And after that, we are now ready to convert real numbers to a digital representation. So digital representation, and in the end, we do the opposite. D2A converter, and there is a compensated reconstruction filter, which we briefly talked about when we introduced D2A conversion a few weeks ago. So let me summarize with you a few practical issues. Okay. The first practical issue is that continuous time signals are not precisely band limited. Continuous time signals, strictly speaking, has extended bandwidth, right? So you need to practically just do the low pass filter, okay? Whenever if you are going to sample your signal next, so it's absolutely recommended that we want to prevent aliasing. Limit your bandwidth first to ensure that there will be no aliasing. Okay, that's one practical issue, number one. And there's another practical issue that ideal low-pass filter actually cannot be realized. What's that about? Ideal low-pass filter, maybe it's we can talk about it. Ideal low-pass filter, does anybody remember ideal low-pass filter has a inverse Fourier transform, right? So ideal low-pass filter in the frequency domain with a cutoff frequency omega c minus omega c in continuous frequency domain. Yeah. When you think about this, back in the time domain, what's the result? Sinc, right? This is a kind of a sinc function. But sinc function, if you really think about it, this is problematic. I said this cannot be implemented. Ideal is ideal. Ideal means it's not real. It's not practical, right? I said that sinc interpolation cannot be implemented. Why? There are a few reasons. First reason is that in the time domain, it extends from minus infinity to infinity. I mean, this property alone makes it impractical. Yeah. This just simply cannot be implemented, right? So keep in mind that this is not the focus of our study right here. I'm pretty sure that A to D conversion has a lot of details that itself is a field, itself is a specialty. If you're really interested in ADC, maybe you may want to speak to Professor Xie Zicheng. I think he specializes in that. So, but keep in mind this, this thing really cannot be implemented. It lasts forever. Cannot be. It needs to be approximated. The best we can do, the best anti-aliasing filter we can do is never ideal. It's an approximation of ideal filter. Okay, all we can do is approximation. So that's the second practical issue. And the third practical issue is that ideal C to D and D to C conversion does not worry about quantization. But now we need to start to worry about it. Okay? We need to start worry about how many bits do we have and how much quantization error that will introduce. Right? So this, again, ideal C to D or D to C are both ideal concepts. Right? In practice, they need to be replaced. They can be approximated by A to D and D to A conversion. A stands for analog, D stands for digital. Right. So with those are a few remarks in mind. So here is the outline for this lecture. So in the next slide, next few slides, I will just briefly first talk about sample and hold. Very simple idea. And then following that, we go to the issue of quantization and the noise it introduces. We'll talk about binary representation of numbers. We'll talk about some properties of the noise that's introduced by quantization, by rounding. Okay? When we represent numbers by binary representations, then we will encounter noise. And we will study the noise property, its distribution and its spectrum. Two different ideas. Okay, so with that, let's talk about sample and hold first. So to sample and hold means you to something right here. Okay. So here, suppose that we have a continuous time signal, and we have a sampling period t. To sample and hold, just literally. Literal means we measure the signal and then hold it. That's all. Yeah. We take a measurement of a signal right here, for example, at this moment, minus 3t, and then hold it. Yeah. And after t, after a period of t, then we repeat the process. We sample the signal. Oh, and we make a measurement right there. The signal is so much. Then we hold. The system holds right there. So that's why it's called sample and hold. Sample and hold. Sample and hold. Sample and hold. Okay? Very simple idea shown in this picture. But why do we hold? We hold that's because then that gives us some freedom to make the conversion. Okay? As long as we can finish the A to D conversion within this much of time, we are fine. Okay? Sometimes it takes longer. Sometimes it takes we're almost running out of time. Sometimes we can just do the conversion right away. Doesn't matter. As long as you can finish the conversion within a period of t, that's okay. Sample and hold. Hold it first, then ask this next block to do the conversion. So that being said, that means everything here is ignored. Okay, anything in between sample time is going to be ignored. Yeah. So that's the idea of sample and hold, so as we can make the conversion. Okay. So what do we mean conversion? Any questions here? Anything? Does everything look okay right here? Very simple idea: sample and hold. Okay. And then so now. That's sample and hold, okay? And that's the overall block diagram. But here, let me say that to perform sample and hold and then convert it to digital domain, these two blocks are equivalent to 2 steps. They are equivalent. They're equivalent to converting to discrete time first, then perform quantization. Okay? Converting to discrete time first, then perform quantization. And quantization, the result of quantization is going to be denoted as using a hat right here. 一个帽子, hat. So let's denote the result after quantization as x hat. And b, here with or without b, it doesn't really matter. But hat means after quantization. Right? So I also need to define a few things, a few terms. First of all is this symbol right here, denoted as xm. It stands for the kind of maximum scale, the full scale, the full scale. Yeah. So let's say xm is you can call it full scale in the sense that we are going to limit our signal between minus of the full scale to plus full scale. The signal is going to be limited. Okay, the signal value is going to be limited from minus to plus that full scale. Everything beyond that range, what can we do? There's nothing we can do. We'll simply clip the signal. 我们就让它截断了. Yeah, okay. We'll simply clip the signal. There will be examples. Okay. So full scale means that your signal may look like this to begin with, but before we talk about quantization, we need to first define what's the desired range. Okay, what's the kind of minimum to maximum range? So let's say our range is going to be plus to minus the full scale. So let's define our full scale to be within this range. So that means that later on we'll see anything that's beyond this, anything that's beyond this is just going to be clipped. Okay, it's just going to be clipped. So now the signal will not be encoded. So anything that's larger than plus m or more negative than minus xm will be simply. We will simply say sorry. We are reaching out of the range. Okay, so that's the meaning of full scale. Okay, so it's an important parameter regarding the design right here. First define the full scale here. Then we can talk about representation. Okay, then finally, in all the samples right here, then we can talk about how do we convert all the samples into a sequence of, let's say, 8 bits, a sequence of 16 bits for every real number right here. Okay? So far, so good? So we have two parameters, one parameter called xm, and the other parameter is denoted as b. That's the number of bits. Okay, essentially the number of bits. And let's look at an example first. Okay, so in the next slide, I'm going to show you an example. So this is an important figure. Okay, let's figure out. We say that this in the textbook says that this is a typical quantizer for discussion for education purposes. Quantizer for AD conversion. Okay, what does that mean? So this is a I/O plot. Input for x, output in the vertical axis. Okay, this is an I/O plot. And what do we see here? What do you see here? Like steps, right? Staircase. It looks like a staircase. 可以这样楼梯嘛 Yeah. So this is an I/O plot. So here on the right, so how do I explain? So first, if you count how many steps right here, what do we have? We have 1 level, 2 level, 3 level, 4, 5 in the middle, 6, 7, 8. 8 levels. Okay, 8 levels can be represented by 3 bits. Yeah? 8 levels can be represented by 3 bits. Okay, so you can now define how are you going to use 3 bits to represent each level. Now we are ready to talk about how we represent each level, but in this example, there are 8 levels. Agree? So 8 level, and we separate the level by a step size called delta, quantization step size. So in the negative end, the output will be minus delta, minus 2 delta, or minus 3 delta, and so on. On the positive side, the output can be 0 for sure, or delta, 2 delta, or 3 delta. So 8 levels. And we have a quantization step size that's, and we are going to represent the output as integer multiple of delta. Okay, 8 different levels. It should be pretty clear, from minus 4 delta to 3 delta. 8 different levels. So far, so good? Huh? All right, so now, 8 different levels. So conceptually, I'm going to say this first. Conceptually, I'm going to say that, okay, since the full range is 2xm, right? 2xm should be equal to, in this example, a times delta. Can we agree on that? Roughly speaking. Roughly speaking. So delta is equal to 2xm divided by a. Now what is a? 8 is 2 to the 3rd power. Okay? So this is a relation between how many bits we have, what's the full scale, and what's the quantization step size. Roughly speaking. Okay, so that's what I'm going to say right here. We have delta equals to that. Okay, 2 times the full scale divided by 2 to the power of how many bits we have. Okay. It's kind of sad that here we really cannot represent 4 delta, right? On the negative side, there's a little remark right here. On the negative side, we were able to represent minus 4 delta. But now we lose the capability to represent 4 delta because that will be an extra level. So there's a bit of asymmetry right here, 不太对称. You represent this side, you lose the ability to represent that side. Okay, that point is something that we need to compromise. But roughly speaking, I want to just share with you 2 times the full scale equals to 8 times quantization step. And 8 here is 2 to the 3rd power. 3 being what? 3 being the number of bits. Okay, number of bits. So now one code for each level. So now there are different options. So here the first option has a name 2's complement. I'm not sure, have you all learned about what's 2's complement? 在哪门课? In which course? Logic design. Oh, great. When I was a college student, there was a class called 计算机概论, Introduction to Computers. You don't have that, right? Good for you. It's a boring class. That's where I learned 2's complement. So this is 2's complement. It's easier to understand. Let's take a quick review here. To the positive side, 0 means 0, right? And this is binary 1, right? So 1 represents 1 delta, 2 represents 2 delta, 3 represents 3 delta. Okay, that's very straightforward. 非常直截了当. But what happened right here? It's like 0, 1, 2, 3, 4, 5, 6, 7. That's the scheme, the 2's complement way of encoding your number. Okay? Encoding the number 0 to 3 and -4 back to -1. Okay? So that's an example, and you can just also generalize what if we have 3 bits, 4 bits, 5 bits, or more bits to represent, to encode your numbers. Still, 2's complement goes from 0 to 1, 1, 1, 1, 1, and back to most negative level, and then it increases, it goes back to 0. Yeah, that's 2's complement. Okay? Take a look, 2's complement. Yeah. And just to take a last look of this figure, we haven't talked about here, right here. What's going on right here? So this relation is going to give you the nearest integer multiple. It's about finding the nearest integer. Okay? For example, here, between 0.5 delta and 1.5 delta, between here, the nearest integer is delta. Right? I mean, the nearest integer multiple of delta is 1 delta. Right? 0.5, 1.5, the nearest integer is 1. Of course, you need to specify what if the value is exactly this. Does it go here? Does it go to the next level? Do we just round up or round down? Yeah? So, but anyway, so the idea, the kind of basic idea is to find the nearest integer. So that's what quantization is about. Quantization is about finding the nearest integer or rounding. Simply in Chinese, 42 rule. Very, very simple. Yeah? So that's why we get a staircase shape right here for quantization. And in next, let's do an exercise. Okay, exercise time. Yeah. Well, so this is the plot to remind ourselves this is what we have when we have 3 bits. But what if we have now 8 bits? 8 bits. And I need you to tell us, help me, what does this encode? What does this code correspond to? What does it represent? How many delta does it represent? Okay, yeah. So I give you some, maybe 2 minutes, and we can check the answer. Right? How many delta does it represent? How many delta? Now we have 8 bits. Suppose that we use 2's complement, by the way. Okay, let's use 2's complement. Okay, so question is, what is this number in 2's complement? What is this in 2's complement? Okay, I'll give you 1 more minute to try to understand this. Check if you understand 2's complement. Okay, does anybody have an answer right now? How many delta? 1, what do we have? 1, 2, 0, 0, 0, 1, 0, 0, 1. Okay. How many delta? First of all, the first bit is 1, right? So this is negative. Okay. First, we want to notice that this is negative. Okay. This is negative. How about here? How about here? In the textbook, it has a formula, actually. This is about if this is B0, B1, each bit. So if this is a sequence, a string, 一个字串, if this is a binary string, denoted as B0 to B7. In the textbook, actually, you find a formula. There is a formula. There is a formula. I hope I can be correct. The formula that this equals to what? Minus 2 minus B0 times 2 to the 0th power, okay? Plus B1 2 to the minus 1 power plus B2, I write one more term. So that's a formula given by, you can find it on the textbook. Okay? But you probably have learned that tooth complement is much more simple than that. Right? It's much more simple. So what do we do? Can somebody tell me? What do we do next? After figuring out it's negative. Tooth complement, right? Tooth complement. What does complement mean? 反过来, complement means opposite. So now the suggestion, a lot of you might have learned this. Let's review. So 反过来, so let's flip the 1 to 0. Whenever you see a 1, write 0. Whenever you see a 0, write 1. Yeah? Okay, tooth complement. Because that's the way what the complete, no, not complete, complement. Okay? Complements means to do the opposite. Okay? To flip 1, you keep the 1 here, but for the next 7 bits, change 1 to 0 and change 0 to 1. Okay? 1 to 0, 0 to 1, 1 to 0, 0 to 1. And then what? And what do we do? And then do the binary representation of these 3 bits, right? So what does it represent? Can anybody tell me? 2加4, 2 plus, 2 plus 4 plus 16 plus 32, right? What's the result? So this is 32 in decimal, 16 in decimal, 4 in decimal, and 2 plus, you just sum them up. What do we have? 54. So the answer is minus 54 delta. Huh? Oh, I forgot to plus 1, right? I forgot to plus 1, yes, thank you. The answer is so I'm, 还要再加1 啊, so you need to add 1. And this should be the same as equivalent to that. Okay? 再加1. So then, so the answer is with the minus sign in the beginning. So the answer is minus 55 delta. Okay? So that's what this string, this binary string, represents in quantization. Right? So that's a nice little exercise, and which corresponds to this formula on the textbook. Yeah, this should be. Yeah, exactly. Yeah. So it depends. So this, I argue this is probably, if you multiply by full range, that might be what it is trying to say. Okay. Because full range, why? Because full range now is going to be 2 to the what? 7th power delta. Full scale. Yeah? Plus or minus full scale, right? And we have 8 bits, which means we have so many levels to represent. I think everything put together, this is equivalent to that. Thanks for pointing out. This is a factor of 2 to the 7th right here. All right, so very good comment. And shall we now move on to the kind of core concept I want you to take home? I want you to take home today that, yeah, sure, quantization is about finding the nearest integer. And secondly, please now try to think about this as something that will introduce noise. There will be quantization error, right? Because quantization is an approximation. We are approximate our real numbers with only 128 different levels. 256, for example. So this is an approximation. By abandoning the fractional part, then we introduce approximation error. And error is, we want to think of error as what is shown in this diagram. Okay? So let's take a look. This diagram shows that when we perform quantization, you can think equivalently as if we have a signal for sure, and then we are introducing error. So that's kind of the key message I want you to take home today and think about it. Okay? Quantization is equivalent to introducing some sort of error because it is an approximation process. Because we are finding the nearest integer, thereby abandoning the fractional part. 小数点以下不看了, right? Well, it's rounding. So finding the nearest integer introduces this error, and we call this error. We can think of error as something being introduced. The two of them add to, and the result is the result has a hat. Okay, so this result is after quantization. X hat as a function of x. Okay, x hat sure is a function of x, but you can equivalently think of it as if x hat is x plus error. Okay, x plus error. So something for you to ponder upon, right? And this is important. Okay? Any comment here? Is it clear what I'm trying to say? Is it clear to all of you? Anybody? Introducing error. Okay, quantization introduces error. Okay, so quantization introduces error. And here is a nice little example on the textbook. Okay, suppose that we have a signal, and it's discrete time. The signal is 0.99 times cosine with a period of something, right? Suppose that this is a signal like that. And then, in this example, how many levels do we have? We have, again, 8 possible levels. 8 possible levels using 3-bit, right? And now suppose that, suppose that our scale, full scale is 1, okay? So we can represent anything from -1 to almost 1, but the last level cannot be encoded. So we need to abandon the last level, the highest level. So maximum now is clipped at 0.75, 0.75. That's the meaning. Okay? When you decide the maximum range, then the signal is going to be clipped. Whenever the signal goes out of the range, okay, it's clipped on top, and it's also clipped, sort of clipped at the bottom. So in this some period of time, you find that the nearest integer nearest level is -1. The nearest level is -1. So that's a kind of a nice little example of what's happening before quantization and after quantization. And of course, it introduces error. Okay? It introduces error. So what is error? Error is defined by the output subtracted by the input. 输出减输入叫做 error. Yeah. So let's take a note. So here, error, quantization error. Error is defined as the output subtracted by the input. That's the definition, the usual definition of error. So therefore, we can think of the input as if that is suffering from some extra thing extra noise right here, and the result is our output of quantization. Okay, output of quantization is denoted as Q of xn. Yeah. So that's the overall picture. Yeah. Before and after quantization. Okay. So in the next slide, we look at the error. Okay. So now, if you just mentally calculate the difference, yeah, that's the error. This thing output subtracted by the input. That's the definition of error. Okay. So the next slide, now we take a look at the error. Error looks like that. The error looks like that. If we subtract the input from the output, okay? 输出减输入, if we subtract the input from the output, this is how the error looks like for this example. Could be positive, could be negative. Okay? Very simple. And this is what? What's that? The next plot is when we have 8-bit instead of only 3 bits. This is the error we have. Okay? Now, this error, the first thing we should notice that is the level, of course, becomes smaller. Yeah, of course, the noise level becomes smaller. Very simple stuff. Yeah, using more bits, you have a finer representation. The error is smaller. Yeah, makes sense, right? So that's from the textbook. So next week, when we come back, we will finish this lecture. But let me just give you a quick preview, okay? So the quick preview is that now from here, you just look at this last plot right there. Does it look random? That's the question. This thing, and compared to 3 bits versus 8 bits, right? I think we can sort of see that this looks more random than that. This thing is not really random. I mean, it's random right here, but now the shape shows up. Right? So it's not really random here, not random here, but maybe in here it looks random. But this looks more random than that. Yeah? Okay? Just by inspection. 用看的嘛, by inspection. By just simply visualizing the error, this thing indeed looks more random. But when we say more random, what do we really mean? Right? Like tomorrow's discussion session is going to be selected randomly. Right? What do you mean random? How random is random? So in probability, this is a few occasions that in this semester that we will need to borrow from probability. Okay, so we need some kind of more rigorous definition when we talk about randomness. Okay, do we mean that it's more uniformly distributed, or do we mean that it's a random process, in which every sample is independent to other samples? Those are already 2 different notions of randomness. 2种关于 random 不同的想法啊。So next week when we come back, we talk about a more rigorous definition of randomness. Are we talking about uniform distribution? Or are we talking about, if it's uniform distribution, we can calculate its expected value and so on, right? Probability, seriously. But there's also other properties that we need to mention. We can talk about whether there's some sequence of error. As a random process, how about its spectrum? Yeah. Is every sample independent of the next sample? If it happens, then we call that is what? Is identical, what? IID. IID. There is what? IID. Identical, independent, identically distributed. All right. Yeah, so there are different notions of randomness that's worth mentioning. But we will talk about that next week when we come back. All right. So tomorrow, please come back here, and we'll have the first follow-up discussion. Okay. Yeah. Thank you for being here, and yeah, class dismissed. 好问题。